Imagine the universe in total darkness, quiet enough that even time seems to be holding its breath. Somewhere far beyond the Milky Way, in a galaxy so distant that its light began travelling before humans existed, before mammals ruled Earth, before many of our mountains had risen, two dead stars are circling each other. They are not ordinary stars anymore. They are the crushed hearts of giant suns, made mostly of neutrons, each one only about the size of a city, yet heavier than our sun. They are spinning around one another faster and faster, drawing closer with every orbit, shaking space itself as if the fabric of reality is being twisted. Then, in the final fraction of a second, they collide. And for one brief cosmic moment, the darkness is torn open by an explosion so extreme that it can be detected across billions of light years. A flash races outward. Gravitational waves ripple through the universe. Gamma rays burst like a silent scream. Heavy elements are forged in the fire. Gold, platinum, uranium, and strange radioactive matter are thrown into space. And the most terrifying part is this. By the time we see the explosion, it may already be billions of years old. What kind of explosion can announce itself across such impossible distances? What kind of object is so dense that a spoonful of its matter would weigh more than a mountain? What kind of cosmic violence can create treasure, destroy worlds, bend space-time, and still leave behind a mystery that modern science has not completely solved? Tonight, we're going deep into one of the most powerful realities in astrophysics, the neutron-star merger, the kilonova, and the gamma-ray burst that can shine across a huge fraction of the observable universe. And while you listen, allow yourself to slow down, because this is not just a story about destruction. This is a story about creation. It is about the hidden origin of matter. It is about the dead stars that may have made the atoms inside your phone, your jewelry, the earth beneath you, and perhaps even the chemistry that allowed life to begin. So stay with this journey, and if this kind of cosmic mystery pulls your mind into the deep, dark beauty of space, then gently like, subscribe, and share your thoughts in the comments as we drift through the story. Because the universe does not reveal its secrets loudly. It whispers them through light, gravity, and ancient explosions. At first, the title sounds almost impossible, a neutron explosion visible across half the universe. It sounds like a myth, like something from science fiction, like a cosmic bomb so bright that every civilization in space would look up and see it. But the real science is even stranger than the myth. The phrase does not mean that a single neutron explodes like a tiny firecracker. It does not mean a normal explosion with flames and smoke. In space, explosions are not like explosions on Earth. There is no air to carry sound. There is no atmosphere to make a fireball behave like the mushroom clouds humans fear. A neutron explosion, in the scientific sense, is the catastrophic release of energy involving neutron-rich matter, the collision of neutron stars, the birth of a kilonova, and sometimes the launching of a gamma-ray burst. These events are so energetic that telescopes can detect them from galaxies billions of light-years away. They are not visible to the naked eye most of the time, and they are not always aimed at us. But when the geometry is right, when a narrow jet points toward Earth, the flash can outshine almost everything else in the gamma-ray sky. For seconds, it becomes a lighthouse from deep time. To understand the explosion, we have to begin long before the flash, inside a massive star. A star is a balance between two ancient forces. Gravity pulls inward, trying to crush everything into the center. Fusion pushes outward, releasing energy by combining light atomic nuclei into heavier ones. For millions of years, a massive star survives by burning one fuel after another. Hydrogen becomes helium. Helium becomes carbon and oxygen. Later, under increasing pressure and heat, heavier elements appear. The star becomes layered like a cosmic onion, with different nuclear reactions burning in different shells. But this cannot continue forever. Fusion gives energy only up to a point. When the core becomes dominated by iron group elements, the star reaches a terrible boundary. Iron does not release useful energy when fused under normal stellar conditions. Instead of supporting the star, the core becomes a dead weight. Then gravity begins its final argument. The iron core collapses. Electrons are forced into protons. Protons and electrons combine to form neutrons and neutrinos. The core shrinks at a speed that is almost beyond imagination, from thousands of kilometers across to perhaps 20 kilometers across. Matter that once floated as plasma inside a star is crushed into nuclear density. The collapse rebounds, neutrinos flood outward, shock waves fight through the star, and the outer layers explode as a supernova. The star dies, but its center remains. If the remaining core is not too massive, it becomes a neutron star. If it is too massive, gravity wins completely, and a black hole is born. A neutron star is one of the strangest objects that nature allows. It's not simply a big ball of neutrons in the way Earth is a ball of rock. Its interior is a layered nightmare of extreme physics. Its outer crust may contain atomic nuclei arranged in solid structures, but as you go deeper, the pressure becomes so great that nuclei are crushed closer and closer together. Electrons become highly energetic. Neutrons drip out of nuclei. Deeper still, matter may behave like a superfluid, with particles moving in quantum states that have no ordinary comparison. Near the center, scientists still do not know exactly what exists. Maybe neutrons remain as extreme nuclear matter, maybe hyperons appear, maybe quarks partially break free, maybe there are phases of matter we have never recreated on Earth. The neutron star is not only an object, it is a laboratory made by gravity. Its density is almost insulting to ordinary intuition. A teaspoon of neutron star material, if somehow removed and kept stable, could weigh billions of tons. The gravity at its surface is so intense that mountains cannot grow high. A mountain on a neutron star might be only millimeters tall, yet contain enormous mass. Light leaving its surface is stretched by gravity. Time near it ticks differently from time far away. Its magnetic field can be billions or trillions of times stronger than Earth's. Some neutron stars spin hundreds of times per second, sending beams of radiation into space like cosmic lighthouses. We call those pulsars. A pulsar may look rhythmic and controlled, but it is the corpse of a giant star, rotating with the precision of a clock because angular momentum has been locked into a city-sized object heavier than the Sun. Now comes the first twist. A neutron star by itself is already extreme, but the most universe-shaking event often requires two of them. How do two neutron stars end up together? The answer begins with a binary system. Two massive stars born orbiting each other. They live, evolve, exchange material, swell, strip each other, explode, and somehow the system survives not one supernova, but two. Each explosion can kick the remnant violently. Many binaries are broken apart, but in rare cases the two dead cores remain bound. What remains is a pair of neutron stars orbiting in the darkness, like two tiny anvils of nuclear matter locked in a gravitational dance. For a long time, nothing obvious happens. They may orbit each other for millions or billions of years, but they are not truly stable. According to Einstein's general theory of relativity, accelerating masses can emit gravitational waves, ripples in space-time itself. These waves carry away energy. As the binary loses energy, the orbit shrinks. The neutron stars spiral inward, slowly at first, then faster. The rhythm tightens. If you could translate gravitational waves into sound, the signal would rise like a chirp, increasing in pitch and intensity as the stars close in. The universe is not silent in gravity, it sings. But it sings in space-time, not air. The final moments are almost too fast for the mind. Two objects heavier than the Sun, each about the size of a city, orbit each other hundreds of times per second. Their surfaces are stretched by tidal forces. Their magnetic fields twist and reconnect. Their crusts may crack. Neutron-rich matter is pulled outward in long tidal tails. The boundary between two stars becomes meaningless. They crash, shear, tear, and merge. In less than a second, a new object forms. Maybe a massive neutron star that survives for a short time, maybe a hypermassive neutron star supported temporarily by rotation and thermal pressure, or maybe a black hole that appears almost immediately. Around it forms a disk of debris, hot, dense, neutron-rich material swirling at relativistic speeds. This is the neutron explosion. It is not a simple detonation. It is gravity, nuclear physics, relativity, magnetism, and radiation all acting together in a single cosmic wound. Some matter is flung outward at a significant fraction of the speed of light. This ejected material is rich in neutrons, and that matters deeply. In normal stars, building elements heavier than iron is difficult because it often requires adding neutrons, and then allowing radioactive decay to turn some neutrons into protons. In a neutron-star merger, there are neutrons everywhere. Atomic nuclei can capture them rapidly, one after another, before they have time to decay. This is called the rapid neutron-capture process, or R process. It is one of the main ways the universe creates many of its heaviest elements. Think about that slowly. In the moment of collision, matter does not merely explode, it transforms. Atomic nuclei become swollen with neutrons. They decay into heavy elements. Radioactive isotopes heat the expanding debris. The glow that follows is called a kilonova. It is not as bright for as long as a typical supernova, but it has a special signature. It reddens over days as heavy elements, especially lanthanides, absorb and reprocess light. It is a cosmic forge visible from far away. The explosion is a graveyard and a birthplace at once. Here the story becomes intimate. The gold on Earth was not made in Earth. Gold cannot be cooked inside ordinary stars in large amounts by normal fusion. Platinum, uranium, and many heavy elements require extreme neutron-rich environments. Neutron star mergers are one of the major known sources. Some heavy elements may also come from rare kinds of supernovae, but neutron star mergers are proven factories of R process material. That means a ring, a circuit board, a medical isotope, the iodine in your body, the heavy atoms buried in Earth's crust. All of them may carry the memory of events like this. Before the solar system existed, ancient explosions seeded the gas cloud from which the sun and planets formed. The violence happened first, the calm came later, but the kilonova is only part of the spectacle. In some mergers, a jet is launched. Imagine a newborn black hole or a short-lived massive neutron star surrounded by a blazing disk. Magnetic fields twist. Matter falls inward. Energy is channeled along the poles. Two narrow beams erupt in opposite directions at nearly the speed of a light. These jets punch through surrounding debris. If one of them is pointed toward Earth, we see a short gamma ray burst, a flash of the most energetic light in the electromagnetic spectrum. Gamma rays cannot be seen by human eyes, but space telescopes can detect them. And because the emission is so concentrated, the burst can appear unbelievably bright across cosmic distances. This is where visible across half the universe becomes scientifically meaningful, but we must be careful. The observable universe is about 93 billion light-years across in present-day diameter, because space has expanded while light has travelled. When we say something is visible across a huge fraction of the universe, we usually mean detectable by instruments from billions of light-years away, not visible like a star in the night sky. Long gamma-ray bursts produced by collapsing massive stars have been detected from extremely early cosmic times, when the universe was only a small fraction of its current age. Short gamma-ray bursts, associated with neutron star mergers or neutron star black hole mergers, are harder to see at great distances because they are brief, but they can still be detected across cosmological scales when bright and aligned. A neutron star merger with a jet pointed right at us could send a signal across an enormous portion of the observable universe. Its light would travel for billions of years, stretched by cosmic expansion, weakened by distance, but still carrying the unmistakable signature of extreme physics. The second twist is that the explosion we observe is never happening now in the everyday sense. If a burst is detected from a galaxy billions of light-years away, the event happened billions of years ago. The stars may have collided before Earth had complex life, or before the Sun existed, depending on the distance. The light only arrives now. Every distant explosion is a time capsule. We are not watching the present, we are watching the past finally touch us. The universe is not a live broadcast. It is an archive made of light. One of the most important real examples of this kind of event was GW 170817, detected in 2017. It was not across half the universe. It was much closer by cosmic standards, about 130 million light-years away. But it changed astronomy forever because it was the first event where scientists detected gravitational waves from a neutron star merger and also saw light from the same source. The gravitational wave detectors heard the spacetime chirp. Then space telescopes detected a short gamma-ray signal. Observatories around the world searched the sky and found the kilonova in a galaxy called NGC 4993. For the first time, humanity did not merely see the universe. It saw and heard the same cosmic collision through different messengers. That event proved something profound. Gravitational waves travel at essentially the speed of light. Neutron star mergers can produce short gamma-ray bursts. Kilonova can forge heavy elements. Multi-messenger astronomy was no longer a dream. It had become reality. The universe had sent us gravity, light, and nuclear chemistry in one package. And yet, even that nearby event raised new questions. How exactly was the jet launched? Did the merger first form a hypermassive neutron star before collapsing into a black hole? What is the true structure of the jet? How much gold and platinum were made? What does the gravitational wave signal reveal about the internal stiffness of neutron star matter? The explosion answered old questions and opened deeper ones. The internal stiffness of neutron star matter may sound like a technical detail, but it is one of the biggest mysteries in physics. If nuclear matter is stiff, neutron stars can be larger for the same mass. If it is soft, they are more compact. During a merger, the way the stars deform under each other's gravity depends on this internal structure. Gravitational waves carry that information. In other words, when two neutron stars collide, they do not only make an explosion. They broadcast the behavior of matter at densities no laboratory can fully reproduce. Each merger is a message from the edge of known physics. Now imagine the final second more closely. The two stars spiral inward. Their orbital speed becomes a large fraction of the speed of light. Space is warped violently. The stars are not perfect solid balls. They are fluid objects with crusts, magnetic fields, and superdense interiors. Tidal forces stretch them. Matter is ripped away. Some ejecta comes from tidal tails flung out by orbital motion. Some comes from shock-heated material squeezed between the stars at collision. Some comes later from winds blowing off the accretion disk. Each component has different speed, composition, and neutron richness. These differences shape the kilonova's color and brightness. The blue light often comes from material with fewer lanthanides, allowing shorter wavelength light to escape more easily. The redder glow comes from lanthanide-rich material, whose complex electron structures create high opacity, trapping and reprocessing light into infrared. That is why a kilonova changes color. It is not just cooling like a coal, it is revealing the chemistry of newly forged matter. The color is an elemental fingerprint, and then there is the jet. Not every neutron star merger produces a gamma-ray burst visible to us. The jet is narrow. If it points elsewhere, we may see only a weaker off-axis afterglow, or no gamma rays at all. This means the universe may be full of hidden mergers that do not shout directly at Earth. We detect only some of them. The brightest bursts are not necessarily the most powerful in total energy. They may simply be aimed at us. This is another cosmic twist. Brightness is not only about power, it is also about alignment. Sometimes the universe appears dramatic because we are standing in the beam. The beam itself is not like a laser made of clean light from the beginning. It is a violent relativistic outflow, a jet of particles and energy pushing through merger debris. As it travels, it interacts with surrounding material, producing shocks. Electrons are accelerated, magnetic fields guide radiation. Gamma rays flash first, then X-rays, optical light, radio waves, and infrared afterglows may follow. The event evolves from seconds to days to weeks to months. A burst that begins as a blink becomes a fading ember in many wavelengths. Astronomers chase it across the spectrum. The gamma-ray burst is astonishing because gamma rays are the universe's sharpest, most energetic photons. Human eyes see only a narrow band of light, but gamma rays are far beyond violet, far beyond X-rays, with energies associated with nuclear and particle processes. Earth's atmosphere protects us from most gamma rays, so we need space observatories to detect them. When a detector in orbit records a sudden flash, scientists must quickly ask, was it a cosmic explosion, a solar flare, a magnetoflare, or something else? Timing, spectrum, location, and follow-up observations reveal the truth. Short gamma-ray bursts typically last less than about 2 seconds, though the classification is not perfect. Long gamma-ray bursts usually last more than 2 seconds and are often linked to massive star collapse. But nature is messy. Some bursts blur categories. Some short bursts have extended emission. Some long-looking bursts may come from compact object mergers. The universe does not organize itself for human convenience. Our categories are useful, but the cosmos keeps reminding us that reality has edges we have not mapped. The third twist is that a neutron-star merger is both tiny and enormous. The physical objects are tiny compared with stars, city-sized remnants. The final collision occurs in a region smaller than many countries on Earth, yet the energy released can affect spacetime across the universe. The gamma-ray signal can cross billions of light-years. The heavy elements can seed future planets. The gravitational waves expand outward forever, growing weaker but never truly disappearing. A city-sized object can write across cosmic history. Think about the energy scale. The sun shines steadily for billions of years, converting mass into light. A neutron-star merger releases an enormous amount of gravitational energy in a moment. Much of it goes into gravitational waves, neutrinos, heat, kinetic energy, and radiation. The gamma-ray burst alone, if assumed to be emitted in all directions, would imply absurd energies, but because the emission is beamed, the true energy is more manageable, though still extreme. The beaming is why a distant burst can appear so luminous. It concentrates the energy into a narrow cone, like focusing a flashlight beam instead of lighting a whole room. But even this analogy is weak. A flashlight beam travels through quiet air. A gamma-ray burst jet tunnels through debris moving near light speed, shaped by magnetic fields and relativistic effects. Time itself behaves strangely for material moving so fast. Radiation is boosted in the direction of motion. The jet appears brighter and more energetic to observers in front of it. Relativity does not merely describe the burst, it helps create what we see. Now let us slow down and look at the word neutron. A neutron is electrically neutral, found in atomic nuclei alongside protons. Alone outside a nucleus, a free neutron decays after several minutes on average into a proton, an electron, and an antineutrino. But inside neutron stars, neutrons are packed so densely and stabilized by gravity and degeneracy pressure that they can exist in vast numbers. Degeneracy pressure comes from quantum mechanics. Fermions, such as neutrons, cannot all occupy the same quantum state. When squeezed, they resist compression, not because they are tiny hardballs, but because quantum rules force them into higher momentum states. In a neutron star, quantum mechanics becomes a pillar holding up a star against gravity. But even degeneracy pressure has limits. If the mass is too high, gravity overwhelms all support, and collapse to a black hole occurs. The exact maximum mass of neutron stars is still uncertain, though observations of heavy neutron stars above 2 solar masses constrain the possibilities. A merger can briefly create an object above the normal limit because rapid rotation and heat provide extra support. But as energy is lost and angular momentum redistributes, collapse may follow. That collapse may be central to launching a jet. The birth of a black hole may happen inside the explosion, hidden behind light and matter. This means the neutron explosion might contain a black hole in its heart. From the outside, we see the flash, but deep within, spacetime may have sealed part of the story behind an event horizon. Matter spirals into darkness. Magnetic fields thread the disk. Energy escapes along the poles. The universe creates a signal by feeding material into a region from which no light can return. It is one of the most poetic contradictions in physics. A black hole can power one of the brightest explosions in the universe, not because light escapes from inside the horizon, but because matter outside the horizon releases tremendous energy before falling in. The merger also releases neutrinos, ghostly particles that interact weakly with matter. In the dense environment of the collision, neutrinos and antineutrinos are produced in enormous numbers. They carry away energy and affect the neutron-to-proton ratio in the ejector, influencing which elements form. Neutrinos are usually almost invisible to us, passing through planets and bodies with ease. Yet in the merger, they help sculpt the chemistry of the debris. Invisible particles shape visible gold. Now consider the expanding ejector. It is radioactive. Newly formed unstable nuclei decay, releasing heat. That heat powers the Kilonova glow. The brightness and color depend on the amount of material ejected, its velocity, its composition, and its opacity. Scientists compare observed Kilonova light curves to models to estimate how much R-process matter was produced. GW170817 suggested that a significant amount of heavy material was thrown into space, perhaps enough to make many Earth masses of precious metals, though exact numbers depend on models. This does not mean there are nuggets of gold flying around like coins. It means atoms and nuclei are mixed in expanding debris, later to be incorporated into interstellar gas, future stars and planets. The process is slow after the explosion. The debris expands into the galaxy. Over long timescales, it mixes with interstellar matter. New generations of stars form from enriched gas. Planets condense. Heavy elements become minerals, cores, atmospheres, oceans, and biological chemistry. Violence becomes geology. Radioactive ashes become worlds. A neutron star merger might last seconds, but its consequences can echo for billions of years. There is another twist hidden in the timing. Neutron star mergers may occur long after the stars that created them were born. Massive stars live quickly, but after two neutron stars form, their in-spiral time can vary enormously. Some merge within millions of years, others take billions. That means a process enrichment can occur early or late in a galaxy's history. Scientists study old stars with unusual heavy element abundances to understand when and where such events happened. Some dwarf galaxies appear to preserve chemical fingerprints of rare enrichment events. By reading starlight, astronomers reconstruct ancient explosions that no telescope saw directly. Starlight is forensic evidence. Every absorption line is a clue. Every abundance pattern is a fossil. When a star's atmosphere contains europium or other R-process elements, it may be carrying the ashes of a neutron-rich catastrophe. The star itself may be calm, ancient, and quiet, but its chemistry remembers violence. Now return to the idea of visibility across cosmic distances. Light weakens with distance, spreading over a larger sphere. The farther an event is, the dimmer it appears. Cosmic expansion also stretches light, shifting wavelengths toward redder energies. Time intervals appear longer because of cosmological time dilation. A burst that lasted 1 second in its own frame may be observed as longer if it occurred in the distant universe. Its photons also arrive with lower energies than when they were emitted. Yet gamma-ray bursts are so luminous that, even after these effects, they can be detected from extraordinary distances. They are among the universe's most distant beacons. When astronomers detect a high redshift burst, they are seeing a period when the universe was younger. Redshift is not simply a Doppler shift from motion through space. In cosmology, it largely reflects the expansion of space itself. As light travels, its wavelength is stretched with the universe. The higher the redshift, the earlier the epoch we're observing. A burst from extreme redshift can illuminate the young cosmos, even helping probe the material between galaxies. In that sense, a gamma-ray burst is not only an explosion, it is a flashlight shining through cosmic history. Could a neutron star merger be seen from half the universe? The honest answer depends on what we mean. If we mean by human eyes, no, not normally. If we mean by sensitive space telescopes detecting gamma rays and afterglows, then extremely energetic, favorably beamed events can be visible from billions of light years away, across a vast fraction of observable cosmic history. If we mean gravitational waves, current detectors are more limited for neutron star mergers than light-based gamma-ray detectors, though future detectors may reach much farther. So the title becomes a doorway. The real wonder is not exaggeration, but the fact that nature produces events even close to such a claim. And this is important. Science does not become less amazing when we remove falsehood. It becomes more amazing. A fictional explosion visible across the universe is entertaining. A real neutron star merger, detectable through gravitational waves, gamma rays, kilonova light, X-rays, radio waves, and chemical fingerprints is deeper. It is not a single flash. It is a multi-layered message. It speaks in gravity, radiation, particles, and atoms. Now imagine a civilization in another galaxy, with telescopes pointed at the same burst. Their instruments record the flash too, but at a different time depending on their location. The same explosion becomes part of many histories. To one world it may be ancient, to another it may not have arrived yet. There is no universal now that all observers share across cosmic distances. Relativity and light travel time fracture simultaneity. The explosion is one event, but its arrival is scattered through space-time. The universe is full of such delayed meetings. A photon emitted in a gamma-ray burst may travel for billions of years without interruption, passing between galaxies through expanding emptiness, near clusters that bend its path slightly through gravitational lensing, until finally it strikes a detector built by beings on a small rocky planet. That detector converts the photon into data. Data becomes a notice. Scientists wake up, point telescopes, compare signals, write papers, update models. An event that lasted seconds becomes decades of human investigation. The explosion also reminds us how fragile our view is. If the jet is not pointed at us, the gamma-ray burst may be missed. If telescopes are not watching the right region, the afterglow may fade. If the event is behind dust or too distant, details may be lost. Astronomy is partly patience and partly luck. The universe does not arrange its most important events for our convenience. We build networks of detectors because the sky is too large and time is too short. A neutron-star merger also has an afterlife in radio waves. As the ejector and jet interact with surrounding gas, shocks can accelerate particles and produce synchrotron radiation. Radio telescopes may detect the slowly evolving remnant long after the initial flash. This delayed radio glow can reveal the energy and geometry of the outflow. In GW 170817, radio and X-ray observations over time helped scientists understand that the event involved a structured jet seen off-axis. We were not staring directly down the jet. Instead, we observed it from an angle, which made the gamma-ray burst unusually faint compared with classical short bursts. This taught us that many mergers may be hidden in plain sight, appearing different depending on our viewing angle. Viewing angle is everything. The same explosion can look like a brilliant short gamma-ray burst, a faint off-axis burst, a kilonova without a detected gamma-ray signal, or perhaps only a gravitational wave chirp if optical follow-up fails. Reality is one event. Observation is perspective. That idea is almost philosophical, but it is also hard astrophysics. Now let us explore the danger. What if such an explosion happened nearby and its jet pointed at Earth? A close gamma-ray burst could damage atmospheres, alter chemistry, and increase radiation exposure. Long gamma-ray bursts from massive stars are often discussed as possible threats if close enough and aimed correctly. Short bursts from neutron-star mergers could also be dangerous if extremely nearby and aligned, but such events are rare. Space is vast. The probability of a devastating nearby, directly aimed burst is low on human timescales. Still, the possibility reminds us that life exists under a cosmic sky that is not always gentle. Earth is protected by distance, atmosphere, magnetic field, and luck. But distance also gives us beauty. If the explosion is far enough, it is not a threat. It becomes a message. The same physics that could destroy a nearby atmosphere becomes, from far away, a signal that teaches us how the universe works. Cosmic violence becomes knowledge when filtered through distance. Now there is a deeper question. Why do neutron stars merge at all? The cause is gravity, but the path is history. A binary system must survive 2 stellar deaths. It must receive just the right kicks. It must remain close enough for gravitational waves to shrink the orbit within the age of the universe. This makes each merger the result of a long chain of improbable conditions. When we detect one, we are not seeing a random flash. We are seeing the final page of a story that began with 2 massive stars born together in a cloud of gas. They lived, burned, expanded, exchanged matter, exploded, survived, spiraled, and finally collided. The burst is the last sentence of a billion-year biography, and after the last sentence comes a new book. The ejected material travels outward. Some may escape the host galaxy, some may enrich nearby star-forming regions, some may remain in hot gas for ages. Eventually, heavy elements join new systems. A planet forms, oceans appear, chemistry unfolds, maybe life begins. In that way, neutron star mergers are not only endings, they are ancestors. This is why the phrase, "we are made of star stuff," is true but incomplete. Some of us is made of ordinary stellar fusion, carbon, oxygen, nitrogen. Some is made in supernovae, some is made in neutron-rich catastrophes like mergers. We are not only star stuff, we are explosion stuff. We are merger ash. We are the cooled remains of processes so violent that they shook space-time. The fourth twist is that the brightest event may begin in darkness. Before the merger, the binary neutron stars may be invisible to ordinary telescopes, especially if they are old and no longer active pulsars pointing beams at us. They can orbit silently for ages. But gravitational waves reveal them. The final in spiral emits a signal that detectors can catch before or around the time light arrives. This gives astronomers a new sense, not vision, but gravitational hearing. Traditional astronomy sees electromagnetic radiation. Gravitational wave astronomy senses the motion of mass itself. A neutron star merger is one of the few events that can speak both languages. The detectors that hear these waves are extraordinary. Laser interferometers measure changes in length far smaller than the size of a proton over kilometer-scale arms. They must isolate vibrations from earthquakes, traffic, thermal noise, quantum noise, and countless disturbances. When a gravitational wave passes, spacetime stretches one arm and squeezes the other by a tiny amount. The signal is buried in noise, extracted through careful analysis, and matched to predictions from general relativity. The fact that humans can detect such tiny distortions caused by objects colliding millions of light-years away is itself almost unbelievable. But it is real, and each detection improves our understanding of the cosmic population of neutron stars. How often do they merge? How are their masses distributed? Do they usually form black holes after merging? How much matter do they eject? Are they the dominant source of our process elements, or do rare supernovae also contribute significantly? The answers are still being refined. This is living science, not a closed chapter. Now focus again on the collision. During the merger, temperatures can reach billions of degrees. Matter is compressed and heated. Neutrinos flood the environment. Magnetic fields may be amplified to unimaginable strengths by turbulence and differential rotation. The remnant may ring like a bell in gravitational waves at high frequencies, though current detectors struggle to observe those post-merger signals clearly for most events. Future detectors may capture them and reveal the internal physics of the remnant. One day, the sound after the collision may tell us whether exotic matter exists inside neutron stars. Exotic matter is not fantasy here, it is a scientific possibility. At extreme densities, particles that are unstable or rare under normal conditions might become energetically favorable. Hyperons, deconfined quarks, color superconducting phases. These are not confirmed inside neutron stars, but they are possible under theories of dense nuclear matter. The merger is a natural experiment probing whether matter remains nuclear or changes identity under pressure. When two neutron stars collide, they may briefly create the densest observable matter in the universe outside black holes. That phrase matters. Outside black holes. Black holes hide their interiors behind event horizons. Neutron stars show us extreme density without hiding everything. They are cosmic laboratories because light and gravity can escape from their surroundings. A neutron star merger may create a black hole, but before the horizon swallows the central remnant, the matter's behavior influences gravitational waves and ejecta. The universe gives us a glimpse before closing the door. Now let us think about the speed of the ejecta. Some material can be launched at tens of % of the speed of light. That is fast enough for relativistic effects to matter. A piece of matter moving at 0.2 times the speed of light travels about 60,000 kilometers per second. In 1 second, it crosses distances larger than Earth's circumference. In a minute, it can travel millions of kilometers. The Kilonova debris expands rapidly, becoming thinner and cooler. As it expands, photons gradually escape. The glow rises and fades on timescales of hours to days, unlike supernovae, which often evolve over weeks. This fast evolution is one reason rapid follow-up is critical. Wait too long, and the blue light may be gone. The color evolution is like a cosmic sunset, but powered by radioactive decay instead of atmosphere. Blue to red, hot to cooler, transparent to opaque in complex ways. The light tells us that the debris is full of heavy atoms with tangled electron structures. The universe paints the signature of the periodic table across the sky. The fifth twist is that the explosion may solve a mystery inside Earth. Why does Earth contain heavy elements at all? The early universe after the Big Bang mostly made hydrogen, helium, and traces of lithium. Heavier elements required stars and stellar deaths. But the heaviest elements required special conditions. Without our process events, the periodic table would be poorer. No natural gold veins, no uranium decay heating planetary interiors in the same way, fewer heavy elements for technology and geology. The neutron explosion is not remote from human civilization. It is hidden inside civilization's materials. Uranium and thorium, produced by our process channels, contribute to radioactive heat inside rocky planets. That heat helps drive geological activity over long timescales. Plate tectonics, volcanism, magnetic field generation, and planetary evolution depend on internal heat sources, including leftover formation heat and radioactive decay. The connection is indirect but profound. A merger in deep space can help shape the thermal fate of planets billions of years later. Gold is emotionally powerful, but scientifically the story is broader. Europium, platinum, iridium, xenon, iodine, tellurium, and many rare heavy nuclei all matter. Some are used in technology, some appear in biology in traceways, some are markers in stellar spectra. The R process is not a jewelry factory, it is a cosmic expansion of complexity. Now imagine the aftermath around the merger site. If a black hole remains, it may be small by black hole standards, only a few solar masses. Around it, the accretion disk drains, winds blow, the jet fades, the kilonova cools. Eventually the site becomes dark again. The galaxy continues rotating, stars continue shining. To any nearby observer, the event would have been catastrophic. But from far away, it becomes a fading point of light. The universe absorbs even its greatest violence into silence. But the gravitational waves keep traveling. They spread outward at light speed, weakening with distance. Long after the light has faded, the spacetime ripple continues crossing the cosmos. It may pass through planets, stars, nebulae, and empty voids, changing distances by tiny amounts. Most worlds will never notice, but if an advanced detector is waiting, the ripple becomes a story. This brings us to another mystery. Why was GW1708, 17's gamma-ray signal, delayed by about 1.7 seconds after the gravitational wave merger time? That delay can be explained by several factors. The time required to launch the jet, the time for the jet to break through surrounding ejecta, and the location where gamma rays are produced. It also confirmed that gravitational waves and light travel at nearly the same speed over cosmic distances, placing strong constraints on some alternative theories of gravity. A tiny delay after a 130 million year journey became a powerful test of fundamental physics. That is one of the most beautiful things about astronomy. A difference of seconds can test laws across millions of years. A faint glow in another galaxy can reveal nuclear processes. A burst can tell us about gravity, matter, chemistry, and cosmic expansion all at once. The universe is interconnected in ways that make every observation bigger than it first appears. Now let's look at the human side. When a gamma-ray burst detector triggers, alerts go out rapidly. Robotic telescopes respond. Astronomers search error regions. Some events are localized well, others are difficult. Optical telescopes look for new points of light not present before. Infrared observatories track reddening. Spectrographs break the light into wavelengths. Radio dishes wait for late afterglow. X-ray telescopes monitor high-energy emission. The event becomes a global pursuit. No single telescope owns the truth. The truth is assembled from many instruments, many wavelengths, many teams. This multi-messenger approach is the future of astrophysics. In the past, humans mostly studied the universe through light. Then came cosmic rays, neutrinos, gravitational waves. Each messenger has strengths and weaknesses. Light is rich in detail but can be blocked or delayed. Neutrinos escape dense regions but are hard to detect. Gravitational waves pass through almost everything but require extreme precision to measure. Together, they reveal events that none could fully explain alone. A neutron-star merger is perfect for this because it is dense, energetic, and luminous. It produces gravity waves from mass motion, electromagnetic radiation from heated and accelerated matter, neutrinos from nuclear processes, and heavy elements from neutron-capture. It is not one phenomenon, it is a convergence. Now let us consider the word explosion again. On Earth, explosions are driven by chemical energy, nuclear energy, or pressure differences. In a neutron-star merger, the dominant energy source is gravitational binding energy. Matter falls deeper into curved spacetime and releases energy. The conversion efficiency can be enormous. The explosion is not powered by burning fuel in the ordinary sense. It is powered by the geometry of spacetime and the rearrangement of mass under gravity. Gravity, the force we think of as gentle because it holds us to the ground, becomes the engine of cosmic violence. Gravity is weak between small objects, but it is always attractive and acts over long distances. In massive stars, it shapes life and death. In neutron stars, it compresses matter to nuclear density. In mergers, it accelerates city-sized masses to relativistic speeds. The same force that makes a dropped leaf fall can make space-time ring when enough mass moves fast enough. Scale changes everything. The sixth twist is that neutron stars are not truly dead in the simple sense. They are stellar remnants, but they remain active physical systems. They spin down, they cool, they glitch. Their crusts may crack, their magnetic fields evolve. Some become magneators, with magnetic fields so intense that they can produce giant flares. Magnetar flares are another kind of high-energy transient, and the strongest could be detected from other galaxies. But for the title's deepest meaning, the neutron star merger is the main event. The explosion where neutron-rich matter is torn open and transformed. Magnetars deserve a moment because they reveal how extreme neutron star magnetic fields can be. A magnetar flare can release in a fraction of a second more energy than the sun emits in hundreds of thousands of years, depending on the event. These flares are thought to come from magnetic stress and crustal fractures. They are not the same as Kilonova, and they do not forge heavy elements in the same way. But they remind us that neutron stars can be dangerous even without merging. A neutron star is not a quiet corpse, it is a compressed engine. Still, a merger is different because it destroys the binary system itself. Two remnants become one remnant or black hole. The event is irreversible. Before, two orbiting neutron stars. After, a new compact object, expanding debris, and a changed galaxy. In the final seconds, the system loses its identity. The dance becomes collision. The collision becomes light. The light becomes history. Now picture a photon from the burst. It is born in a region of unimaginable energy. It travels outward through expanding material, perhaps after being produced by shocks in a relativistic jet. It escapes the host galaxy. It enters intergalactic space. It crosses voids where there may be less than one atom per cubic meter. It passes near galaxies whose gravity slightly curves its path. The universe expands during its journey, stretching its wavelength. Meanwhile, on Earth, continents shift, species evolve, civilizations rise, languages form, telescopes are invented, satellites are launched. Then the photon arrives and is absorbed in a detector. Its journey ends as a data point, but that data point carries the birthmark of the explosion. We often think seeing is immediate. We open our eyes and the world appears. But cosmic seeing is delayed intimacy. The farther we look, the older the story. A neutron explosion across billions of light years is not just far away in space, it is far away in time. Its light is ancient, but its arrival is new. That tension makes astronomy feel almost dreamlike. Now let us go deeper into our process, nucleosynthesis. In ordinary nuclei, protons repel each other because they have positive charge, but the strong nuclear force binds protons and neutrons at very short ranges. Neutrons help add nuclear binding without adding electric repulsion. During the R process, seed nuclei capture neutrons rapidly. They move far from the valley of stability, becoming extremely neutron-rich. Then beta decay converts neutrons into protons, moving the nuclei towards stable heavy elements. The path depends on neutron density, temperature, expansion rate, and nuclear properties of unstable isotopes, many of which are hard to measure in laboratories. This means Kilonova observations also test nuclear physics far from stability. The heavy elements are not created in a neat sequence like a factory assembly line. The process is chaotic, statistical, and deeply quantum. Nuclei capture, decay, fission, and recapture. Some very heavy nuclei may split, feeding material back into lower mass ranges. The final abundance pattern can show peaks corresponding to nuclear shell effects. When astronomers compare these patterns to elements observed in old stars, they learn about the universality or diversity of our process sites. The explosion becomes a periodic table experiment with a galaxy-sized laboratory. Now think about the sheer contradiction. The most delicate things can be born from the most violent. A gold atom is stable and quiet. It can sit in a wedding ring for generations, but its origin may involve matter torn from neutron stars at relativistic speeds, radioactive decay, and a flash brighter than galaxies. Stability is not always born gently. Sometimes peace is the cooled shape of chaos. The seventh twist is that the explosion may be visible across the universe because it is not equally visible in every direction. This seems strange at first. We imagine a spherical blast, energy spreading evenly. Kilonova ejecta is more broadly distributed, though not perfectly spherical, but gamma-ray bursts are strongly directional. If you are inside the beam, the burst is brilliant. If you're outside it, it may be faint or invisible in gamma rays. That means an event's apparent brightness can differ enormously for different observers. Somewhere else in the cosmos, another civilization might see the same merger as a blazing burst, while we see only a faint afterglow, or vice versa. The universe is full of hidden asymmetries. Stars are spheres only approximately. Explosions are not perfect balls. Magnetic fields create axes. Rotation creates disks. Jets create beams. Observations depend on angles. The sky is not only a map of objects, it is a map of perspectives. Now consider what happens if the merger leaves behind a long-lived neutron star instead of promptly forming a black hole. A stable or supramassive remnant could inject extra energy into the ejecta, changing the kilonova light curve. It might produce extended X-ray emission or other signatures. If it collapses later, that collapse could leave an imprint. Scientists search for these clues to understand the remnant's fate. The maximum mass of neutron stars is tied to this question. Each merger is a scale weighing nuclear matter under extreme gravity. The fate of the remnant depends on total mass, equation of state, rotation, thermal pressure, and mass loss. A prompt collapse may eject less material and produce a different signal. A delayed collapse may allow more matter to escape. A long-lived neutron star may energize the debris. This complexity is why no two mergers are exactly identical. Nature repeats themes, not copies. Now let us look at the surrounding galaxy. Neutron star mergers can occur far from the bright star-forming regions where their original massive stars were born. Because supernova kicks can push the binary system, and because inspiral times can be long, the merger may happen in the outskirts of a galaxy or even outside the visible stellar disk. Some short gamma-ray bursts have been found offset from their host galaxies. That location is a clue to their origins. A massive star collapse usually happens near star-forming regions because massive stars die young. A neutron star merger can happen after wandering for ages. So when astronomers locate a burst far from a galaxy's center, they ask, did a compact binary travel there before merging? What was its birth kick? How old was the system? The explosion's position becomes part of the biography. The eighth twist is that the explosion teaches us about expansion of the universe. Gravitational wave events with electromagnetic counterparts can act as standard sirens. The gravitational wave signal gives information about distance, while the host galaxy's redshift gives information about cosmic expansion. By comparing them, scientists can estimate the Hubble constant, the current expansion rate of the universe. This is still difficult because of uncertainties and limited events, but the method is powerful. A neutron star collision can help measure the size and expansion history of the cosmos. That means one explosion can connect the smallest and largest scales, neutrons inside nuclear matter, and the expansion of the universe itself. Few phenomena span such a range, from femtometers to gigaparsecs, from quantum states to cosmology, from milliseconds to billions of years. Now let us imagine the event from nearby, though safely as a thought experiment. The two neutron stars approach. Their gravity distorts any surrounding matter. The sky near them would be warped by gravitational lensing. Light paths bend. If there were an accretion disk or debris, it would glow violently. In the final moments, the gravitational forces would rip apart anything nearby. There would be no sound, but space-time would vibrate. The collision would produce radiation lethal at close range. The gamma-ray jet, if aimed at you, would be annihilating. Yet from far away, the same event appears as a delicate dot. Scale turns terror into beauty. Distance turns destruction into astronomy. Time turns catastrophe into origin. Now let us address a common misunderstanding. A neutron star merger is not the same as a supernova, though both involve stellar death and extreme energy. A supernova is usually the explosion of a star or white dwarf. A neutron star merger is the collision of compact remnants already formed by earlier supernovae. The merger may produce a kilonova, which is powered by radioactive decay of freshly synthesized heavy elements and is typically faster and differently coloured than a supernova. The gamma-ray burst may accompany the merger if a jet forms and is aligned. These distinctions matter because each event tells a different chapter of cosmic evolution. Another misunderstanding is that neutron stars are made only of neutrons with no other particles. Real neutron stars contain a mix depending on depth: nuclei, electrons, free neutrons, protons, possibly muons, and exotic particles in the core. The term neutron star reflects the dominance of neutron-rich matter, not absolute purity. Science names are useful, but reality is richer than names. Another misunderstanding is that all heavy elements come from neutron star mergers. The truth is still being studied. Neutron star mergers are confirmed R-process sites and can produce large amounts of heavy elements. Some rare supernova-related environments may also contribute. Different elements and different cosmic times may involve multiple sources. The universe usually does not rely on only one pathway. It builds complexity through overlapping processes. Now, let us return to the title's emotional center, visible across half the universe. What does it mean for anything to be visible at all? Light must be created, escape, survive the journey, enter our instruments, and be recognized. Visibility is not just brightness, it is survival. The photon must avoid absorption, the signal must rise above noise, the detector must be watching, the data must be interpreted correctly. A cosmic explosion is visible only when nature and intelligence meet across distance. That meeting is fragile. A gamma-ray burst can last less than a heartbeat. If the detector is not operating, if Earth blocks the view for a low-orbit instrument, if the localization is poor, the first clue may vanish. But networks help. Satellites watch large portions of the sky. Ground telescopes respond. Data archives preserve signals. Human coordination extends our senses. The ninth twist is that some of the explosion's most important information is invisible to ordinary sight. Gravitational waves have no color. Neutrinos pass unnoticed. Gamma rays cannot be seen by eyes. Radio waves are silent. Infrared is hidden from human vision. Yet together, these invisible messengers create the real picture. The universe is far more than what eyes evolved to detect. Human sight is a tiny window. Science is the act of building more windows. A neutron star merger would be almost incomprehensible to unaided senses. No sound reaches us. No visible flash may appear in the night sky unless it is close and bright enough. But instruments reveal the hidden drama. This is why modern astronomy feels like translating a language. The universe speaks in wavelengths, particles, and spacetime distortions. We decode. Now think of the cosmic web. Galaxies are not scattered randomly. They trace filaments and clusters separated by voids. A burst from a distant galaxy travels through this structure. Intervening matter can absorb certain wavelengths, lens light, or imprint features. The explosion becomes a backlight for the universe between there and here. In some cases, afterglows of gamma-ray bursts help probe gas in distant galaxies and intergalactic space. The death of stars becomes a tool to study matter that would otherwise remain invisible. This is another transformation, an explosion as a lamp. A burst destroys locally but illuminates cosmically. It reveals its host galaxy, intervening absorbers, cosmic chemical enrichment, and the conditions of early epochs. The universe uses violence to make itself readable. Now let us explore how a binary neutron star system loses energy through gravitational waves more intuitively. Imagine two skaters spinning around each other on frictionless ice, but every turn sends a tiny ripple through the ice that carries away energy. They move closer. As they move closer, they spin faster, which sends stronger ripples, which makes them move closer even faster. This feedback accelerates until the final plunge. In space, there is no ice, but space-time itself carries the ripples. The energy loss is real. The orbit decays. The merger is inevitable once the system is close enough. The first indirect evidence for gravitational waves came from binary pulsars, especially systems where timing showed orbital decay matching general relativity's predictions. These observations were a triumph before direct detection. Then direct detections of black hole mergers opened the gravitational wave era. Neutron star mergers added light. The sequence shows how science builds: prediction, indirect evidence, direct detection, multi-messenger conformation. Now consider the masses. Neutron stars often have masses around 1.2 to 2 times the mass of the Sun, though exact populations vary. Compress that into a radius of roughly 10 to 15 kilometers, depending on the equation of state. The escape velocity from the surface is a significant fraction of light speed. If you stood there, which you could not, gravity would flatten you beyond any survival. Atomic structures themselves would not remain normal. The surface is not a place in the human sense. It is a boundary of extreme matter. During merger, these compact masses convert orbital energy into gravitational waves with tremendous efficiency. The chirp signal encodes the chirp mass, a combination of the two masses that determines how the frequency evolves. By measuring the waveform, scientists infer masses and sometimes tidal deformability. The signal is a mathematical fingerprint of the system. Hidden in a tiny vibration of mirrors on Earth is the mass of dead stars in another galaxy. This should make us pause. The universe is not only beautiful visually, it is mathematically beautiful. The curve of a signal can reveal invisible masses. The timing of waves can confirm relativity. The color of a fading point can reveal lanthanides. The shape of an afterglow can reveal a jet. Every detail is a clue. The 10th twist is that the explosion's brightness may be less important than its message. A supernova can be brighter optically for longer. A quasar can shine for millions of years. A galaxy contains billions of stars. But a neutron-star merger carries a unique combination. Dense matter, gravitational waves, heavy element creation, relativistic jets. Its importance is not only in luminosity, it is in completeness. It ties together entire branches of physics. This is why scientists were so excited by the first multi-messenger neutron-star merger. It was not just another explosion, it was a Rosetta Stone. It translated between gravity and light. It connected short gamma-ray bursts to mergers. It confirmed Kilonova models. It showed R process signatures. It constrained the speed of gravity. It helped estimate cosmic expansion. One event did the work of many discoveries. Now, imagine future detectors. More sensitive gravitational wave observatories may detect neutron star mergers much farther away and in greater numbers. Space-based detectors will explore different frequency bands. Those stellar mass neutron star inspirals are mainly ground-based targets near merger. Next-generation ground detectors could hear deeper into the universe, possibly detecting vast populations of compact mergers. New wide-field optical surveys will search rapidly for Kilonova. Infrared telescopes will better capture red emission from heavy elements. Gamma-ray monitors will watch for bursts. The future sky will be alive with alerts. As detections grow, scientists will move from individual stories to population statistics. How common are mergers in different galaxy types? How does the rate change over cosmic time? How much R-process material do they contribute overall? What fraction produce successful jets? How often are jets choked, failing to break out but still energizing debris? What remnants survive? Each event will be a sentence. Together they will form a cosmic library. Now let us consider choked jets. A jet launched inside dense merger ejector may fail to escape fully. Instead of producing a classical gamma-ray burst, it deposits energy into surrounding material, creating a cocoon. This cocoon can still produce emission, especially for off-axis observers. The structure of jets and cocoons is an active area of study. The explosion is not simply either jet or no jet. There can be gradients, angular structures, and energy distributions. Again, nature resists simple boxes. A structured jet means energy and speed vary with angle from the axis. Observers at different angles see different brightness and time evolution. This concept helped explain observations of GW170817's afterglow. Rather than a uniform top-hat jet, the outflow likely had angular structure. In cosmic explosions, geometry is destiny. Now let us look at the host galaxy environment. The age and metallicity of the stellar population can reveal clues about the binary's delay time. If the host is an old elliptical galaxy with little star formation, the progenitor system likely took a long time to merge. If the host is a star-forming galaxy, the delay could be shorter. The distribution of events across host types informs models of binary evolution. Each burst location is a fossil record of stellar life cycles. Binary evolution itself is complex. Massive stars can transfer mass. Their envelopes can engulf companions in common envelope phases, shrinking orbits dramatically. Supernova kicks can tilt and stretch orbits. Stellar winds remove mass. Metallicity affects wind strength. The path to a merging double neutron star is narrow and uncertain. The final explosion is dramatic, but the prehistory is equally fascinating. The 11th twist is that before the neutron stars merge, they may be almost perfectly predictable, then in the final moment become violently nonlinear. For millions of years, orbital decay follows smooth equations. Then contact occurs. Hydrodynamics, turbulence, shocks, magnetic instabilities, neutrino transport, nuclear reactions, and general relativity all interact. Simulating the merger requires supercomputers and sophisticated physics. Even then, uncertainties remain. The universe can run the experiment effortlessly. We struggle to model it. The difficulty of simulation is not failure, it is evidence of richness. Dense matter physics, microphysics, and relativistic gravity all matter simultaneously. Few problems in astrophysics are so demanding. Neutron-star mergers sit at the intersection of disciplines that are usually separate. Nuclear physics, plasma physics, relativity, high-energy astrophysics, cosmology, computational physics. One explosion forces them into one room. Now imagine the first milliseconds after merger. If a hypermassive neutron star forms, it rotates differentially, meaning different parts spin at different rates. Magnetic fields are wound and amplified. The object may oscillate violently. Gravitational waves at high frequencies may be emitted. Mass is shed into a disk. Neutrinos cool the remnant. If collapse to a black hole occurs, the central engine changes abruptly. The disk remains briefly, feeding the jet. The entire sequence may unfold faster than a blink, yet it determines the later glow for days and weeks. The universe is full of events where the shortest moments decide the longest consequences. A fraction of a second determines the abundance of gold. A delay of seconds tests gravity. A flash of gamma rays triggers months of observation. A collision of city-sized stars enriches galaxies for eons. Now let us talk about the speed of light and why no flash, however powerful, lets us see instantly. Light speed is the cosmic speed limit for information in vacuum. The gamma rays from a burst do not cross the universe instantly. They travel at light speed, and if the source is billions of light years away, they take billions of years to arrive. When we say the burst was visible across vast distances, we mean its photons survived the journey and remained detectable. The explosion did not illuminate the entire universe at once. It sent a shell of radiation outward, and different places encounter that shell at different times. This shell expands like a growing sphere. Any planet, telescope, or dust grain at the right distance and direction may be crossed by the signal. For beamed gamma rays, the intense shell is concentrated along jet directions. Outside the beam, other emissions may still spread more widely. The event's visibility is a moving boundary through spacetime. Now there is something meditative about this. Somewhere a burst's light is still traveling. It has not reached some galaxies yet. It has already passed others. The explosion is over at its source, but its presence is still unfolding across the cosmos. In relativity, an event's influence is its future light cone. A neutron-star merger writes itself outward into the universe at light speed. We may see only one arrival, but the event's story continues wherever its signals go. The 12th twist is that when we detect the explosion, we become part of its story. The photons end in our instruments. The gravitational wave changes our detector lengths. The signal enters human records. It affects theories, careers, textbooks, and imaginations. A dead star collision becomes a thought in a living brain. Matter forged in ancient explosions built the planet that built the telescope that detected another explosion. The universe observes itself through structures it created. This sounds poetic, but it is physically grounded. Human bodies contain elements made by stars and stellar explosions. Our technologies use heavy elements from cosmic nucleosynthesis. Our detectors are made from matter processed through astrophysical history. When we study neutron-star mergers, ancient matter is measuring ancient matter. Now let us consider how rare these events are in a single galaxy. Neutron-star mergers are far less common than ordinary stellar events like novae, and likely much rarer than core collapse supernovae in a Milky Way-like galaxy. But the observable universe contains enormous numbers of galaxies. Rare events become common when the volume is vast. Gamma-ray monitors detect bursts because they sample a huge cosmic volume. Gravitational wave detectors detect mergers within their sensitivity horizon, and as sensitivity improves, the number rises sharply because volume increases with distance cubed. Looking deeper means seeing far more universe. This is why cosmic rates can feel paradoxical. An event may be rare near us, but frequent somewhere in the observable universe. The sky seems calm because space is enormous, and most events are distant or faint. Instruments reveal a universe flickering constantly with transients. Supernovae, flares, tidal disruption events, gamma-ray bursts, fast radio bursts, variable stars, mergers. The static night sky is an illusion created by human eyes and short lifetimes. Now think about a neutron star merger in a galaxy halfway across observable cosmic history. By the time its light arrives, its host galaxy may have changed dramatically. Stars have died. New stars have formed. The merger remnant may have long faded. The region may be unrecognizable. We detect a message from a place that no longer exists in the same form. Astronomy is communication with ghosts. But ghosts can be truthful. The light carries physical information from the moment of emission. Spectra, timing, polarization, brightness evolution, all preserve clues. The past is not gone if its light is still traveling. It is distributed through the universe, waiting to be intercepted. The 13th twist is that these explosions may help answer whether gravity behaves exactly as Einstein described under extreme conditions. So far, general relativity has passed many tests, including gravitational wave observations. But scientists continue testing because extreme systems can reveal deviations if they exist. Neutron star mergers are especially valuable because they involve strong gravity and matter, not just vacuum black hole spacetime. If gravity couples to matter differently than expected, or if gravitational waves dispersed in unusual ways, signals could reveal it. The near-simultaneous arrival of gravitational waves and gamma rays from GW 17-817 strongly constrained many modified gravity ideas. One collision eliminated broad classes of possibilities. This is how science advances, not only by confirming what is true, but by narrowing what can be false. The universe runs experiments at scales we cannot build. We wait, detect, and learn. Now let us move inside the expanding Kilonova again. As radioactive nuclei decay, electrons and gamma rays deposit heat. The ejector opacity controls how quickly photons escape. Lanthanides and actinides have complex atomic structures with many possible transitions, making the material highly opaque. This is why infrared observations are crucial. If telescopes only look in visible light, they may miss much of the glow, especially for lanthanide-rich ejecta. The heavy elements hide their own birth in red light. That image is profound. The more complex the atoms, the more they reshape the light. Chemistry affects astronomy. Atomic physics affects cosmic color. The periodic table is not only a list in textbooks, it is an optical engine in exploding debris. Now consider the role of polarization. Light can carry information about magnetic fields and geometry through polarization. Measuring polarization in such faint, fast events is difficult, but it can help reveal a symmetry. Future observations may use polarization to understand jets, ejecta shapes, and magnetic fields. Every property of light becomes a clue: brightness, color, timing, direction, polarization. The 14th twist is that the explosion is brief, but preparation takes generations. The stars that become neutron stars must form in molecular clouds. Massive stars synthesize elements during their lives. Supernovae create neutron stars. Binary dynamics shrink or preserve orbits. Gravitational waves slowly drain energy. Only after this long preparation does the merger happen. The flash is sudden only because we ignore the build-up. Many cosmic events are like this, a moment that contains a history. Human life is similar in perception. We see sudden outcomes and miss the slow causes. Astronomy teaches patience. Catastrophe often has a long fuse. Now let us imagine the two neutron stars as clocks. Pulsars can be timed with incredible precision. In a binary system, pulses arrive slightly earlier or later, depending on orbital motion, relativistic effects, and gravitational fields. Pulsar timing has revealed neutron star masses and tested relativity. Some double neutron star systems are known in our galaxy and will merge far in the future. They're quiet countdowns. Their explosions are not for us to see soon, but their timing tells us they are real. One famous system, the Hulse-Taylor binary pulsar, provided strong indirect evidence for gravitational waves through orbital decay. Other systems, like the double pulsar, offer exquisite tests of relativistic gravity. These are not mergers yet, but they are previews. They show that neutron star binaries exist and that gravitational radiation brings them closer. Now let's talk about the afterglow in more detail. A relativistic jet plows into external medium, sweeping up gas. This decelerates the jet and converts kinetic energy into radiation. Electrons accelerated in shocks spiral around magnetic fields, emitting synchrotron radiation. The afterglow can be seen in X-ray, optical, and radio bands, depending on conditions. Its brightness over time reveals the energy, density of surrounding gas, and viewing angle. For off-axis observers, the afterglow may rise slowly as the jet decelerates and its emission cone widens, then peak and fade. This behavior was crucial for interpreting GW170817. The afterglow is the universe showing us not just the explosion, but the explosion's struggle with its environment. Light is produced where fast material meets slow material. The boundary becomes luminous. Motion becomes radiation. Now the 15th twist. Sometimes what we do not see is as important as what we see. If a gravitational wave detection has no electromagnetic counterpart, it could be because the source was too far, poorly localized, hidden by the sun, observed too late, or because the merger involved black holes with little matter. If a neutron star merger produces no bright kilonova, maybe little material was ejected, or the viewing angle and opacity made it hard to see. Non-detections constrain models. Silence has information.